Hi guys, I promised a video about the user interface of the Solar BMS, and I'm just starting this video, but I suppose it will be a very long video, so I apologize for this. But if you got one of these from my website or from Kickstarter, it will be a good idea to watch the entire video, so you know how to use it and don't break it in a way or another, so, or damage your batteries or something like that. So the user interface, that this is the first thing you will see is that I introduced a key lock, and by default right now it enters in this state after 1 minute, but I will change this to as default to a higher count, probably 5, 10, maybe even 15 minutes, so you will not get bothered by this. But during testing right now I leave it to 1 minute, so I know that it will not mess anything else up. I don't know if key lock was really necessary for since these keys seems to perform quite well. They don't get unwanted clicks from noisy environments or something like that. But just in case, I introduced this function, and you can deactivate this if you don't like it. Anyway, let's start. So in order to deactivate this, you need to push 3 keys in a certain order. So I need to push OK, up and down key to unlock the keyboard, the touch keys. So you can do it in sequence like this, or you can probably even swipe like this. So I will start with the last menu and go up because it seems more appropriate. It will work better in explaining things. So the last menu is about, this is really not important. It's just a model number. It can only be 4080 or 1616. For the 1616, the PCB will look the same, so you will see here the 4080 mark. But in software you will see that it's 1616, and it's not just a software limitation. The load MOSFET, it's a different one. It's a smaller one. So you can of course exchange that with the one that I use in the 4080 and just upload the new software. And actually the shunt resistors, they also have different values for the 1616, so it can measure more accurately the current. So you will need to change those two if you want to upgrade to 4080 from a 1616 Solar BMS. Anyway, there's nothing else here. It's a software version. As you can see, it's 0.9. It's almost ready. And hardware version, it's the same thing. It's the 0.3C version. And yeah, just the time that it's not set. It's just okay. So diagnostic, you will probably not use this unless you want to change the software in some ways and you need to see what's going on. This is what I used during development, but I decided to leave it here for those that really want to play with the software and maybe write their own version or modify this or anything like that. What you can see in here, it's the EEPROM content of the main IC, the ESL 94203, and this is in the last column, and the column in the middle, it's actually the parameters in the list that you will see soon after, and they should match if you wrote everything correctly in the main IC. And this is the EEPROM part, and after that, starting here, it's the RAM content. Of course, the RAM is just in the IC. There is nothing to change there, or if I change something that's not in the parameters, these are cell voltages, currents, things like that. So yeah, I think that's it. Maybe these numbers here are also for development. These are it's actually the current reading from the PV. The first one is from the PV input. You see that's right now it's 47. This is digits, so it's not amps or anything like that. And the next is the calibration value when you power this up. I will explain that. When you power this up, it will take a reading of the currents. You should not have anything connected on the PV or on load, and then we'll use those values as offset, because the ADC and whatever the analog part has in there has different offsets for each individual IC, so I needed to implement this calibration part at the start. Okay, I think this is it about this. Nothing else to say about. Then the next menu is device set, and here, okay, here there are quite a few things to explain. Time and date, this is not a big deal. This is just for you to set a time and date initially, and of course when you connect this to a battery, it will stay there for maybe forever, for the life of the battery, I don't know. So once you set this, it will stay there, but it doesn't have an internal backup battery for the time. It makes no sense to have one, since it will anyway be permanently connected to a lithium battery normally. So anyway, so you can set a time and date here, and that's about it. Then LCD touch key and touch key. This is for the backlight and for the key lock that I just explained before. You can set a time when the touch key will be locked. If you put this on on 0, then it will be deactivated. So now it's deactivated, but let's move it up actually, so it doesn't bother us. Okay, and then this is the backlight. Again, this is the time after which the backlight will turn off automatically, and it will turn on again when you push any key. But it was set to 1 minute, let's set it to 5. This is the default when you power it up. But and this is the backlight level. I think I explained this before. It's off and medium and high. I don't know if you can see anything on camera. I have quite strong lights here, and the backlight is not that powerful. I wanted to save power with this, but you will see it if it's dark. It's no problem. Okay, and then let's talk about serial data logging. You have, by default, it's set at the baud rate is set at 9.6K, but you can change this at any value, not just the standard values, but any value, because microcontroller uses the internal clock, which is not extremely precise. So if you see that you have missing data or something like that, you can change this to something that it's not standard, but it will work better, because the real clock will be the standard one, but you set here a different one, and that will correct for the internal oscillator of the microcontroller. But it seems to work fine at the standard, but just in case there is a problem, you could change here in very small steps. Okay, and what I should say about this, okay, I changed the opto-isolator because those that I initially chose were really slow. I chose those for to save power, but those were really bad idea for this kind of speeds. So I chose a different opto-isolator in here for both transmit and receive. And you can, with 1 kilo ohm load on the outside, you can go up to, I think it's 57 something K baud rate, and you can go to the maximum 115.2 K if you use I think around 500 ohms as load, else you will have problem with the communication. But so yeah, you can use anything from 1.2K up to 115K as baud rate, but you should choose the external load. I mean, it's a resistor connected to 3.3 volts, and you should choose that accordingly. As look, here is the an USB to serial. You can find this on eBay. It's, I don't remember the price, but it's really inexpensive. And you just need a resistor as a pull-up from 3.3 volt to RX line, a receive line. And the receive line in here, the pin 1, is actually the transmit line of this Solar BMS, but I use this type of marking because most people want to know exactly what to connect and where, and so you just connect this RX pin, the receive pin, from here to RX pin in here, so there is no confusion for some people. I would have preferred to have pin 1 TX like transmission, but I did that on the beta sample, but I've seen some people really confuse this. Anyway, nothing will happen if you don't connect this the right way, but it will just not work. So just connect it the other way around, and it will work. And the ground X, the pin 3 that you will be using, that it's fully isolated. It has nothing to do with the ground of the battery or anything. It's so the communication part, it's fully optically insulated up to, I don't know, 5000 volt or something. It's really not important. But yeah, that's it, I think, about this. And the interval, this is where you set how fast should the Solar BMS send data to the serial port. The lowest it's 1 second, and you can go as high as I think I put the limit to 3600, so up to 1 hour interval. I don't know what you will want to use. Probably 30 seconds, the default one, it's fine. But just in case you can use higher or lower 1 second if you want. The step it's 1 second. So okay, and of course you need to start the data logging by switching this to 1. Once you push OK, it will send how to call this, a header, so you know what you will have in a table. If you save this in a CSV file, then it's a good idea after you start the terminal recorder on your computer to come here and start data logging, and then you will have a nice header that will tell you what is in each column. Okay, I think that's it about this. MicroSD, this is not implemented, like I said. I didn't have time for this, and I didn't promise I will implement this anyway, but maybe it will be done in the future. I will work on another project next, and that one will use this very similar hardware, the same microcontroller, so maybe I will implement for that one SD data logging, and then I can just make an upgrade and have data logging for this one. Hardware is done, but I think it's done. I hope I didn't make any mistake. I didn't have any time to check the microSD hardware, but if I implement in the next project, I will make sure to include it here also. Anyway, and this was also a request from you guys, from some of the backers. I have added some additional I/O pins in the back here. I will show you later, and you can use those for different purposes. The default one is that you use these two pins as low voltage and high voltage disconnect pins, so it will be actually a mirror of what this MOSFET transistor will do. So the charging and discharging MOSFETs, if X1 is for charging and X2 pin is for discharging, so they will actually output a signal based on what's the state of these two MOSFETs, charging and discharging MOSFETs. So you can use external relays or external MOSFETs for higher discharge or charge capabilities, and but of course you will use some functionality like state of charge cannot be calculated if you have external relays or a transistor, because you will pass current outside of the Solar BMS, so he will not be able to tell what sort of current goes in or out of the battery. But other than that, it should work fine. It should also work for the case where you want to use two Solar BMS for a larger battery bank, for the 48 volt battery. I don't know, maybe you can use even more than that. More than two, I mean, 3 or 4, but I didn't test that. It's just a theory, but I think it works. Anyway, so if this is on 1, as it is on default, this is how it will work, but you can also have this on 2, which means it will not be a mirror of the charging transistor, but it will be used something like an alarm. So you can set a high state of charge alarm for X1 pin, or for X2 pin you can use a low state of charge alarm. So in the case of the X1, when the state of charge is above what you set in here, you can set this to whatever you want. It was default on 90%, but you can set anything. Then you will get a signal on that X1 pin, and on X2 pin you will get a signal if the state of charge is below what is in here on this line. So this may be useful, I don't know, maybe especially the low discharge or a low state of charge. It will be useful to warn you before it will shut down your power. Maybe you have your computer connected, or if it's an off-grid system like it's mine. So I will definitely use this to warn me in case that SOC drops below a certain level. Okay, so we are done with this submenu, and now parameters set. Now here there are quite a few things to say, but let's start with the first thing. Cell type. You have 7 predefined cell type. The first 2 are for lithium iron phosphate, and look, if I change this to 2, it's still lithium iron phosphate, but if you notice, the over voltage is set higher on these parameters than on these ones. And so when you select this with OK and change to something else, it will modify all 35 parameters below. You cannot see all, but you can scroll down and see it will change all this based on battery type. And the scroll-in help, which is available almost in any menu, will explain for which type of battery each of these numbers correspond to. Like in this case 5, it's for lithium cobalt, so normal lithium ion, and 6 and 7 are for supercapacitors. First it's for 2.3 volts type of supercapacitor, the other one is for more common 2.7 volt. So when you don't understand exactly the parameter, you just look at this scrolling help, and should give you enough information to understand what each part is about. Anyway, next, number of cells. This is always set at 8 by default, but you can change this from 3. This is the minimum. You cannot use less than 3 cells because the voltage will be too low for the... And this is the limitation also from the main IC, not just from my design. So, and again, the cells are not connected. If you use, for example, 3 cells, it's not cell 1, 2, and 3. It's cell 1, 2, and 8. And this is again the way that they built this dedicated IC. And but if you check the again the scrolling help, it will tell you which, depending on configuration, which cell you need to connect, and the other one will be just shorted. I will probably make a diagram and show you how this is done, but you can also check the datasheet of the ESL 94203, and then they will explain also there how you need to connect for different cell configurations. Okay, let's leave this to 8, and actually cell type, let's put here, no, actually let's leave it on battery, because this is more common and what you will probably use. But anyway, you need to set here the capacity of your battery, and the reason for that, you need to use here the real capacity, like maybe you have 100 amp cells, but maybe are bad quality or old, and they only have, let's say, 85 amp hour. You should set that value in here, because this is used to calculate the state of charge. So it needs to know what's the real value. If you don't actually know, you can use whatever it's written on battery, like 100 amp hour, but then you'll notice that your battery will be empty maybe, and the state of charge will indicate, let's say 20%, then you'll know that your battery, it's actually a real in real life use just 80 amp hours, and you just came back here and changed this to 80 amp hour, and that will work. Okay, anyway, I forgot to mention, so if you make any change, this is valid in any menu anywhere, and you just change your mind, you just push back, and it will default back to whatever it was here last time if you forgot, and if you push OK, it will stay here. So okay, and this is about the menu and how it's structured, but it's just 6 buttons, and I think the menu is quite easy to use, but I'm a bit biased because I made the menu, so you may not think the same thing about this. Anyway, this is over voltage, and it's not what you think, it's not something bad, it's just the voltage where when any of the cells get to this point, the charging will stop, so it's nothing more, and you can change this with 10 millivolt increments. So and this is the over voltage delay, meaning that it will wait, it's in seconds, so it will wait for 1 second after this threshold was exceeded from on any of the cells, and then it will disconnect the charging. And this is under voltage recovery. It will start charging again when it hits this threshold that you set here. Then this is under voltage. Here it will disconnect the load, and when it gets, any of the cells gets to this level, so the lowest cell will win here. And then again the delay, under voltage delay, again how many seconds to wait. Maybe you have a load that it's just quite harsh on your batteries, and maybe one of the cells will go under 3 volts, but your battery is not discharged, it's just that the load is very heavy for 2 or 3 seconds, and you don't want to disconnect the load, so then you just come here and select how many seconds you want to wait before it cuts off the battery when that under voltage is exceeded, or when any cell is below that set voltage there. And then this is under voltage recovery, when the lowest cell will go above this 3.2 in this case, then the load will be reconnected automatically. Okay, over voltage lockout, this should probably never happen, but just in case you had some wrong parameters in there, like this delay it's very high or something like that, then when it gets to this level it will shut down the charging anyway, so without waiting for any delay or anything like that. And this is the under voltage lockout, same thing. If the battery gets to this level, it will immediately cut off the load. So end of charge, this is an indication in when the highest cell gets to here, 3.47, it will consider that the battery is charged. So and also this is used for state of charge. Initially, when you connect this, it will say state of charge is 50% because it has no idea based on voltage where the state of charge of the battery is. That's why, I mean, for lithium, it's not like for lead acid. You cannot say what's the state of charge just based on voltage. You need to count how much energy you put in and get out of the battery to calculate the state of charge. So initially, the state of charge will be incorrect until you fully charge for the first time your battery, and then it will when it will see that end of charge is flag is set, it will set the state of charge to 100%. Okay, low voltage. It's something must go really wrong to get to this level. But if I don't know, you leave this unsupervised and you lose the solar panel somehow, and the battery gets discharged so low, then the IC will enter a sleep mode where it will use less power, and of course everything by now will be disconnected, charging load especially. And now this is the overcharge current. It's set by default at 48 amps. Of course, this is 40-80, so 40 amps continuous discharge charge and 80 amps continuous discharge. So the overcurrent, it's set 20% higher, and same thing, it's valid for discharge. It's set at 96 amps, so you can definitely use 40 amps and 80 amps. It's not just it's not the limit. The limit is set about 20% higher, and this limit is set in hardware, so the current measurement for the battery, it's done very fast, so you can, in hardware, not in software, cut the load or the charging if these thresholds are exceeded. And you can set here in steps, just 16 I mean, for charging you can start from 4 amps and go up to 48 amps. This is the maximum. There is a 64 amps, but you should not use it. This is just for those that really want to play with, maybe change the MOSFETs, or really want to test the limit of this Solar BMS, but you should stay with 48 amps for charging. Or you can set it lower if you want some kind of protection from a smaller setup. Anyway, again, this delay, it's in milliseconds. It's the time we'll wait after this threshold is exceeded before switching off or cutting of the charging or discharging MOSFET. And the same, it's valid here. And there is a short circuit current also for discharging, of course. And this one, it's set by default at 128, but you can set it higher to 192 if you have any problems. This is not a problem to set it at 192, because this, as you see here, short circuit delay, this is set at very small values, 200 microseconds, so it will act very, very fast and nothing will happen. But especially when you have inductive loads like inverters or motors or something like that, there will be quite serious current spikes when you connect those. So you can set this to 192 if you have any problem, or you can increase this timing. It's set default to 200 microseconds, but you can set it to 400 microseconds or anything up to 1 millisecond. So you can play with this if you have any problem when you connect a load that it's highly inductive and or capacitive actually, and you have high current spikes. You can change this. Okay, this is charge balance. You can set charge balancing for charging or also for discharging if you want to balance the battery faster. Maybe you have very unbalanced cells, and I mean, balancing in this case is not for it will not balance your very unbalanced large battery, but this is to maintain the battery in balance. So initially when you connect the batteries, you should have all cells balanced before manually, and then it will keep them in balance for undefined number of days or years even. I mean, a good battery should not go out of balance with this balancing, even if it's just during charging and it's just 100 milliamps. This is enough to keep even very large cells in balance, despite what other people might think. In fact, I have this the 100 amp hour cells that I have for my house. I balanced them only once since I moved here more than a year ago, manually, and I have no cell balancing. If I will have this, they will never need cell balancing. So okay, and then you have cell balancing minimum and maximum voltage. It's if any cell is outside of these limits, then it will not perform balancing at all, not on just only on those cells, but on any cells. And then you have cell balancing minimum difference. If cells or the difference between minimum and maximum cell, it's smaller than this, than 15 millivolts in this case, it will not perform any balancing, because it's not needed. I mean, the difference is so small, it makes no sense to make balancing. And if the difference between minimum and maximum it's higher than 300 millivolts, again, it will not perform cell balancing, because something is wrong. It should not be a difference this high between cells. So that's why it will not perform cell balancing. You can change this to whatever it's suited for your battery bank, but these are the default values in here. And then you have cell balancing on and off time, and this is in seconds. And what this means is that when a cell needs balancing, it will connect that load resistor on it for 5 seconds, so it will discharge that cells for that cell or many cells depending on the case for 5 seconds, and then it will switch off for 2 seconds, so it can do cell measurement without the voltage drop because of that cell balancing load. So I hope I explained this clear enough. It's not just an analog system, it's a smart digital system, so it can disconnect the cell balancing to make accurate measurements and don't have any voltage drop on the sensing wires. Okay, next one. This is an internal over temperature. It's in millivolt and not in degrees Celsius, because it's not really a linear increment. So I cannot use a simple formula. I will need a table to convert this to degrees Celsius, and plus I don't have any information in the datasheet on how can I do that. I mean, of course I can manually heat the IC to a predefined temperature and then make a table like that way, but it makes no sense, because this, according to the spec, this is the only value they give here. It's this 790 millivolts means I think 115 degrees Celsius, which is anyway very high, and there is no reason for the IC to heat up, because everything, cell balancing and everything is done outside of the IC. IC uses very little power, has absolutely no reason to heat up unless there is something seriously wrong, like a short circuit or a defect on the IC pins or something like that. Other than that, there is no reason for the IC to heat up. Well, it seems that my camera decided to die on me. The battery was dead, and now I need to start again from here. I didn't notice the camera was off, so I was talking with myself for the last 10-15 minutes. Now I think we were here at the internal over temperature, just describing that, and max temperature and mean temperature. This is in binary, and the reason for that is that most people will probably not use the battery temperature as external sensor, because it's not really necessary for lithium iron batteries, or actually not even lithium cobalt batteries if you use them for energy storage. But it will be a long discussion about this, and I just want to finalize this video. I just realized that it will be an extremely long video. I knew it will be long, but this will probably be close to an hour. So yes, it's in binary. You can set a minimum and a maximum, and if it's out of these limits, it will cut the output and the charging. And as you can see, by default they are set at 0 and 4096, which is the maximum in 12-bit, because the values are measured with a 14-bit ADC, but they are, you get in the RAM of the IC, you get only the 12-bit rounded value, so it's okay. And the limits are 0 to 1.8 volt analog, so you can use this for other things, like, I don't know, measuring external current, or I don't know what sort of voltages you may want to measure outside. So you can use this for anything other than temperature, so it's not necessary to use it as temperature. And if you connect a temperature sensor like a thermistor, you normally need a table to know which, if it's not very linear, or you need a formula to approximate the temperature. But you can just hit the thermistor at a temperature that you are interested in, check the value in here that the ADC will output, and then just input those values in here, and you are done. Okay, sleep voltage. This I think I switched to, since last time, to capacitors. so it's not battery anymore. That's why this thresholds seem a bit strange. So let me switch back to battery. So where were we? Here. So it's 2.2. It makes more sense for a lithium iron phosphate battery. So if it reaches, any cells reaches this minimum threshold, it will enter a sort of sleep mode where the main IC uses less power, and this is the delay, 15 seconds, and there are 2 other delays where it enters a much deeper low power mode. And then there is the store button. Now you can store all these changes. Let's make actually some changes like here, so we don't have the default, let's say 72 amp hour, okay, and here 3.54, okay. So and now let's just save this. This will send all the data to the main IC, so it will write the EEPROM with all these parameters in here, but they will not become active until you reset this Solar BMS. And in order to do this, you need to remove the 10-pin connector that it's monitoring individual cells and also powering the Solar BMS. So you just remove this for at least 5 seconds and then insert back, then it will power on, calibrate, and then you are in you have this saved, and when you enter here you see the values that you have in the EEPROM stored when you first enter the parameter setting. So you see it's not a default 100 amp hour, it's 72 amp hour, and the over voltage is 3.54, not 3.55 like this default. So if I go back to 1, and it will give me the default values. But if I get out of here, enter again, I will get again the values that are stored in the actual EEPROM, the current values that the Solar BMS is using. Okay, so that's about the parameter set, and then but now let's change to, I did this again, but okay, I'll need to do it again. We'll use a ultra capacitor because this is what I have connected in here, and if we go into monitoring with the battery thresholds, I will get all kind of strange errors. So okay, let's just yeah, I will just leave all these default and then send this to the main IC, store them actually, and then now we can reset again. Like I said, you should leave this disconnected at least 5 seconds or so. So then you connect this. That garbage on screen is just what I mean, the LCD retains a bit of power and memorizes some of the pixels. That's why it's what you've seen at the startup. Now if you get in here, you see it's the last parameters that I set. Then let's go into monitoring, and what you can see in this first page out of 7 pages of monitoring is the state of charge, which is I think 36%, yeah. But these are ultra capacitors, so the state of charge is done differently than for batteries. You check the battery, the voltage on the lowest cell, and take that voltage and calculate the state of charge. So state of charge is based on voltage, and it's instant. You don't need to first fully charge the capacitor to get the real state of charge. It's much easier for the ultra capacitor to get the state of charge, and it much more accurately than you can get for batteries. Okay, then there is individual cell voltages, and you see that cell 2 and 4 it's highlighted, and that's because these two are the highest and the lowest cell. As you can see, cell 2 is the highest and cell 4 is the lowest, the cell with the lowest voltage. And then you get the difference, the delta between the two, the minimum and the maximum cell, which is around 40 millivolt right now. And you get the total battery voltage, which is 12.32. Okay, so it's locked again. And next page, nothing interesting in here. You just get a bar graph for cell voltages and battery current and battery voltage. That's it. And page 3 you get battery voltage, battery current and bar graphs for them. And then you get internal temperature, TI, that's in millivolt, like I was explaining before. Normally it's around 620 millivolt, and like I said, that this is probably room temperature because there is no heat right now, so I know, maybe 25 degrees Celsius. And already 720 millivolts, it's around I think 115 degrees Celsius, something like that. And then there is external temperature, which is what it reads from the temp E pin in here, the analog value that I was talking about. And now it's floating, so that's why you see that value. But let me just get a jumper, and I will short it to temp O, which is 2.4 volt, and this is used for thermistors, to supply power to thermistors. And you see it's the maximum of the 12-bit value. And if I can get this out, I will put now this to ground, and you see it's yeah, it has a bit of offset, so it's 46. It should be 0, but like I mentioned before, you get a bit of offset with these ADCs, so that's why I need to calibrate for current. And okay, next, okay, locked again. Next, this is page 4. It's a bit more interesting. These are error flags. So if they are highlighted, it means that that particular error it's active. And as you can see in here, it's charge FET and discharge FET are active right now, and I could switch them off with the load button. So I can switch on and off the load and the charging. I need to do this both at the same time, because usually the main IC takes care of the overcurrent and short circuit protection and everything in hardware. So if I manually decide to disconnect the load, for example, without disconnecting the charging FET, then I actually take care manually of everything that happens, so I cannot afford to leave this on when I disconnect the load, the charging. And that's because I don't have any kind of protection. I mean, the software in the microcontroller will need to read everything and take care of this, and I just don't want to do that. So I disconnect both at the same time. Okay, so what the others are, I have first I will there are 15 error flags in here, so I will number them like 1, 2, 3, 4, 5, 6. Okay, so first it's over voltage. So this usually happens when the battery is fully charged. So this, you will see this flag highlighted sometimes. Then it's over voltage lockout, under voltage lockout, IoT it's internal over temperature, COC it's charge over current, DOC discharge over current, discharge short circuit, cell fail, open cell. I mean, if one of the sensing wires it's broken or open, you'll get this error flag. It makes test for this. And then low voltage charging, it means that one of the cells has a voltage too low, so it will not perform charging, and you will need to manually charge that cells and bring it to the over the minimum level, so the charger will start working. But this should never happen unless I don't know, something wrong was going on. And then EPROM correction failed. If you get an error, and writing error, if I don't know, it's very noisy and microcontroller sends wrong data to the main IC, then you will get that flag, but probably never happened. And then I explained charge FET and discharge FET and end of charge, the one in the middle. So that one will also be quite often highlighted, but it's nothing wrong. But with all these error flags, you can investigate if something doesn't is not right. You at least know where to look. So I think that's it. So okay, next page is all about battery. You have battery voltage, battery current, battery power in watt. Then you have two counters, amp hour and watt hour counters, and you can reset these counters if you push OK button. When you are in this page, you will be presented with this submenu, and so you can reset the amp hour counter, watt hour counter independently, or both at the same time, and or none. You can push here OK on none or back, it's the same thing. And next page is almost the same thing, just that it's for the charging, it's for the PV panels. You have again the battery voltage, a PV current, PV charging current, power and amp hour and watt hour counters. And then same thing here, you have load amp hour and load watt hour counters, but this load current, it's actually calculated as the difference between charging current and battery current. So that's it. And again, on the first page, that's it. This is all 7 pages, and I should probably end this video here. So I wanted to say more, but I will probably do another video about hardware and how to connect this properly in which order. Actually, I will tell you right now about how you connect this very shortly. When you first get this, you need to connect the battery first. That's the first thing you need to connect, the battery cable, the positive one. That's it. The ground connections from battery, PV panel and load are all connected outside the Solar BMS together, and the Solar BMS will interrupt the positive lead. So you first just connect the battery, that's it, nothing more, and then you insert this 10 pin sensor connector that measure individual cell voltages, but also powers the solar BMS. This is how it gets the ground and the positive to power this the solar BMS. And then you need to do this because and not have anything else connected, because initially at power up it will check to see what's the offset of the ADC when it measures current. So connecting anything in here will mess that up. So please don't do that. And then you can connect the PV and the load, but before doing that, you probably want to turn off the load so you don't damage the connectors if the load has, let's say, some capacitor, or it's in an inductive load and it cannot be fully turned off like inverters. When you connect an inverter, even if it's turned off from his own button, you will get sparks here when you charge the capacitors inside. So you don't want to damage the connectors, and in order to not do this, you should probably go here to make sure that the FETs are off, you don't have them highlighted. Then connect the PV and the load, and then you can turn them on after you made the connection. So yeah, that's it. But I'll probably make another video about the hardware with a bit more details. But that's it about the user interface. Okay, thanks for watching this video, and probably you will also want to see the other video, the part 2 probably of this video.